focus on Newton's second law and some pretty basic problems, just as a way to introduce ourselves with Newton's second law and become more familiar with the math that we're going to see. So just to recap, Newton's second law states that F equals m times a, which means that if we want to accelerate some sort of mass, we need to have a net force acting on that mass. So we're going to start with two fairly simple problems that both show something kind of different that we can do with F equals m times a. The first one says, how much force does the expanding gases in a gun barrel exert on a 6-gram bullet as it accelerates from rest to 500 meters per second in the 0.7 meter long barrel? Okay. So as always, we're going to start off with what we know and what we don't know. We know that our mass is 6 grams. We know that our initial velocity is 0 meters per second. We know our final velocity should be 500 meters per second, and that the barrel of our gun, or delta x, is 0.7 meters. Okay. And if we go and look at our formula, we see F equals m times a. Well, we're looking for force. That's the ultimate goal of this problem. We know it will be measured in newtons, and we see that we have a mass, and so where's the acceleration? Well, if you remember from our dV/AT equations, we can solve for our acceleration as well. We have all of this information here. We have an initial velocity, final velocity, and a delta x value that we can use to calculate acceleration. Now remember, with our dV/ATs, if we don't have time, we need to use that no time formula. So V final squared equals V initial squared plus 2a delta x. From our knowns and our unknowns, we see that VI is 0, so that's going to cancel out. And we can rearrange this to solve for A. So we're going to have V final squared over 2 delta x. Plug those numbers in, so we're going to have 500 squared over 2 times 0.7. And when you plug this into your calculator, don't be shocked by such a very large number that we're going to get. You have to remember we are accelerating a very tiny bullet throughout a very powerful gun. So when you get an acceleration of 178,571.43 meters per second squared, just know that that is acceptable for a gun. Okay. So now we have our acceleration, we have a mass, we can use F equals m times a. But there's one little catch. If you look at our mass, it's measured in grams. That actually won't work for Newton's second law. In physics, we stick with kilograms for most of our classical mechanics. So when we go in to plug in our mass, we will actually want the kilogram version. So we're going to take the 6 grams, we're going to divide it by 1,000, so that our mass is 0.006 kilograms. We want to use that as our mass. And then we're going to plug in this crazy long acceleration. And that is going to give us our force. So plug that in your calculator. We're going to have a force of 1,071 newtons. And that becomes our final answer for problem 1. So here we use dV/ATs to calculate an acceleration to then plug in our F-net equation. For our second problem, we have a helicopter lifting a 1,250 kilogram car, and the question is asking, what is the tension force in the cable if the acceleration in the system is 1.3 meters per second squared? I have a lot of students jump to a conclusion real quick with this question. They see a mass, they see an acceleration, and they're like, oh, it's just F equals m times a. What they tend to forget is that this is not what the question is asking. F equals ma is the net force, or the sum of all of the forces. The question is actually asking, what is the tension force in the cable that's holding this car up? Okay. So we're going to start this one with a free body diagram. We have 2 forces acting on this car. We know that we're going to have a weight force holding the car down, but a tension force that's lifting it up. Now the key with when we draw our free body diagrams is that our vectors should match the magnitude of our different forces. Because we see that this is a positive acceleration, we are assuming that we are accelerating upwards. That is, they're directly correlated. If we're accelerating upwards, that means our tension force should be larger than our gravitational force, and we can show that with our free body diagram. Okay, so with our free body diagram ready to go, we can actually write our F-net equation. So your F-net equation is going to show all of the forces that are acting on a particular object, in this case, the car. So the car is going to have the tension force pulling it up, and then we're going to subtract the weight force from it, and together they're going to equal mass times acceleration. Okay, so our next step is that we just need to rearrange to solve for tension. So that's going to be ma times plus the force of gravity. And then one thing we can do is we actually know what the force of gravity is. That's the other equation for this unit. F of g equals mass times the acceleration due to gravity. So we'll plug that in, ma plus mg, to get our tension force. Okay. So from there, we know everything. We know our mass is 1,250. We know our acceleration of the system, which is the car that is accelerating upwards, and for gravity. So we can just plug all of those numbers in. And if you notice, I put in a positive 9.81. The reason we do this is because when we were doing projectiles and free falls, the acceleration due to gravity was pointing downwards. The negative indicates a direction. Well, if you notice, we've already included the direction in our F-net equation at the very beginning. Because we said minus Fg, we are saying that Fg acts in the negative direction, so whatever the value or magnitude of that force is going to subtract away from the tension force. So in forces, we typically use a positive 9.81 when we indicate the direction at the very beginning. So you plug all of those in your calculator if you'd like to check it out. We're going to get 13,887.5 newtons. Okay. And so here we have our final answer for the tension force that is holding up this cable. Not just the net force, which we do include, F equals m times a here for our net force, but there's also the force of gravity we have to take into account in this problem.